So in model 4, example number 1, design an angle section when tension members carry a tensile load of 225 kilonewtons. The angle is to be connected to a gusset plate by one of its leg by fillet weld. Use Fu is equal to 410 and Fi is equal to 250 MPa. So in our previous problems we have calculated the design tensile strength of the angle section. But here the load is given, that is tensile load is given. We need to select suitable ISA, Indian Standard Angle section. So let us calculate the numerical problem. So what is step 1? Given data. So what is given here? Tensile load. So P is equal to how much? 225 kilonewtons. Step 2. Design load. So PD is equal to 1.5 into 225. So what is the answer? Let us calculate later. Next, step 3. Permissible stress. So what is the formula for this? Ft is equal to 0.9 into Fi. So what is Fi here? Yield stress. What is given in the question? I think 250 MPa. That is nothing but 250 Newton per mm square. Okay, let us calculate these values. So 1.5 into 225. 337.5. 337.5. 0.9 into 250. 225 Newton per mm square. And units here are 337.5 kilonewtons. What is the next step? We need to find the area. Step 4. Area is equal to design load by permissible stress. That is 337.5 as it is kilonewtons, 10 power 3 divided by 225. So let us find the answer. So 337.5 into 10 power 3 divided by 225. So we got 1500 mm square is the area. So what is required area? We need, as I told you, in step 5 we need to add extra 10% for our safety purpose. Add extra 10% for above area. So what is 10% means? 10 by 100 plus 1 times of 1500. That is 110 by 100 into 1500. So 2 zeros get cancelled. So 15 into 110. So area required is equal to let us calculate this value. So 15 into 110, 1650 mm square is a required area after adding 10% of extra area to the obtained area. So far we have found the tensile load which is given in the question. Later step 2, that is design load. For given above tensile load we need to multiply with 1.5. So step 3, permissible stress. So what is the formula for finding permissible stress? Fd is equal to 0.9 into Fi. Fi is nothing but yield stress. After finding yield stress, step 4, area is equal to design load by permissible stress. We got 1500 mm square. So for step 5, what is step 5 here? For above area, for safety purpose, we need to take extra 10%. So extra 10% means 110 by 100 into 1500. So 2 zeros get cancelled here, and 15 into 110. The area required here is 1650 mm square. After finding this area, based upon this area, we need to select one suitable angle section, whether it may be equal or unequal. If in the question it is given that please choose angle section of equal, means we need to take equal angle. So what is equal angle? As I told you, two sides are equal, whereas unequal angle, two sides are not equal. So ISA means Indian Standard Angle Section. So based after calculation of this area, we should select suitable angle section from your steel table book, whether it may be any of these areas, that may be equal angle or unequal angle. Based upon this required area, after adding 10%, we need to choose or select from your steel table book. After that, the procedure is same as your previous problem. So now let us select one suitable ISA from your steel table book. So step 6, that is area required. So far we have found area required, that is 1650 mm square. So based upon this area, we are going to choose an angle section of 100 into 75 into 10 mm. So based upon this area from steel table book, we got this ISA from steel table book. So let the angle section be 100 into 75 into 10 mm, and this is 75 and this is 10 mm, which is connected to a gusset plate by using your fillet weld. So what is step 7? We need to find design strength due to gross yielding of the section, that is T suffix dg. So what is the formula of design strength due to cross section of yielding? Ag into Fi into partial safety factor 0, that is 1.10. So in this case, again we should not find the area because this is only gross area. Directly we should substitute the area required in the gross area. So gross area for this section is directly we can choose, because based upon this only we have choose ISA 100 into 75 into 10 mm. So that is again we should not or no need to find area again by using that formula. So directly we can write substitute gross area is equal to 1650 mm square. So 1650 mm square is multiplied with 250 divided by 1.10. Now let us calculate the value. So T D G. From here all the design steps are common as your previous problems. So 1650 is multiplied with 250 divided by 1.10. It is divided by 10 power 3, 375 kilonewtons. 375 kilonewtons. So let us assume this as equation 1. Let us write here TDG is equal to how much? 375 kilonewtons. So what is the second step? We need to design strength due to rupture of critical section. So now let us calculate rupture of design strength due to rupture of critical section. So second step 8, design strength due to rupture of critical section. So from page number 32 and 33 from steel table book, that is IS 800 2007, not steel table book, sorry, IS 800 2007 code book 32 and 33. We are going to solve this design strength due to rupture of critical section. So what is the formula for design strength due to rupture of critical section of an angle section? So TDG is equal to 0.9 into ANC into FU by partial safety factor 1, that is we are going to use 1.25. So beta into AGO into Fi by partial safety factor 0, that is nothing but 1.10. So before finding this value we are going to solve for beta. It is very important, right? Before solving this all those step we are going to solve beta. So beta is equal to, what is the formula for beta? 1.4 minus 0.076 by width of the angle section by thickness of the angle section into yield stress of the material by ultimate stress of the material into BS, that is nothing but shear lag distance by length of the weld. It must be greater than or equal to, if ultimate stress is multiplied with 1.10 by 250 is multiplied with 1.25, must be greater than or equal to 0.7. So the value of beta must be lies in between this or this. whichever is smaller we are going to use as a beta value and going to substitute here. So let us solve this. So 1.4 minus 0.076. So what is the width of the, other outstanding length of the angle section? So we have choose, right? We are going to use 100 into 75 into 10 mm, right? So so width of the outstanding leg is 75, where 100 is a longer side which is connected to the gusset plate. So I am going to use 75. 75 is divided by 10 is multiplied with Fi 250 divided by 410 times of Bs. So Bs, yes, outstanding leg and shear leg distance are both are same. So Bs is equal to 75. So LC is not given. So I am using longer side, that is 100. 100 that must be lies in between Fu. What is Fu? 410 is multiplied with 1.10 divided by 250 into 1.25 must be greater than or equal to 0.7. Let us check the value. Let us find the value of beta. So 1.4 minus 0.076 times of 75 divided by 10, 250 divided by 410, 75 divided by 100, that is how much? 1.206. So 1.206 less than or equal to beta value. Let us find this one. 410 multiplied with 1.10, 250 is multiplied with 1.25. So how much? 1.44. Must be greater than or equal to 0.7. Yes. So beta minimum is 1.206, beta maximum is 1.44. So we are going to use beta is equal to 1.206 and we are going to substitute here in this formula. So before substituting we need to find area of connected leg and area of outstanding leg, right? So what is ANC? Area of, so let me solve here. Okay, where should I solve? It's better to solve here, right? So ANC is nothing but area of connected leg. So ANC is equal to B minus T by 2 into T. That is nothing but 100 minus 10 divided by 2 times of thickness of the plate, that is 10. That is area of connected leg. And this one AGO, area of outstanding leg, A minus T by 2 times of T. That is nothing but 75 minus 10 divided by 2 into thickness of the plate. So let us find these both areas. So 100 minus 10 divided by 2 into 10, 950 mm square, because it is an area, right? Next, 75 minus 10 divided by 2 into 10, that is 700 mm square. So after finding beta and area of connected leg, area of outstanding leg, we are going to substitute in this value. So let me substitute. So what is beta value? Beta minimum is equal to 1.206, which we have obtained from using our formula, which is given in page number 32 and 33. So the formula of beta is given there. Please have a look at that. So 0.9 T TDG is equal to 0.9 into ANC, area of connected leg, 950 into Fu 410 divided by 1.25 plus beta 1.206 multiplied with area of outstanding leg, that is 700 mm square into 250, that is Fi divided by 1.10. So 0.9 into 950 into 410 divided by 1.25 plus 1.206 into 700 into 250 divided by 1.10. So what is the area here? If we divide with 10 power 3, so TDG is equal to how much? 472.3 kilonewtons. Is equation 2. So let us write here TD, so not TDG, it is TDN, sorry, TDN is equation 2, right? 472.3 kilonewtons. 472.3 kilonewtons. So far you have calculated or you have found the design strain due to rupture of critical section. So what is the formula for finding rupture of critical section? 0.9 into area of connected leg into ultimate stress divided by 1.25 plus beta into area of outstanding leg into yield stress by 1.10. So before dealing with this, we need to solve area of connected leg and area of outstanding leg and also beta value. From beta minimum or maximum, we are going to choose the beta minimum value for safety purpose. After substituting all these values, we got the design strength due to rupture as 472.3 kilonewtons. Let us assume it as equation 2. Now let us solve design strength due to block shear. Now let us find step 9, that is design strength due to block shear. So again in block shear we are having two formulas, one is TDB1 and TDB2. So whichever is smaller among them, that will be the design strength due to block shear. So the both formulas are same but just reciprocal. Here it doesn't have any 0.9, here we are having 0.9, here we are having 0.9 and here it doesn't have any 0.9. This AVN and this AVG are both are same, that is area under shear. This ATN and this ATG both are same, but everything is same, but we need to solve this. Okay, so AVG, that is nothing but area under shear. So L we are assuming as 100 into T, that is thickness, is how much? We took 100 into 75 into 10 mm, right? So 100 into 10, that is 1000 mm square. Next comes your ATN, that is B into T, that is 75 into 10, that is 750 mm square. Let us substitute these values in above equation. AVG 1000, TDB1 into Fi is 250 divided by root 3 into 1.10 plus 0.9 into ATN 750 into Fu 410 divided by partial safety factor 1.25. Okay, in the same way let us calculate this also. Area under shear L we have assumed as 100, T thickness, that is equal to 1000 mm square. Next ATG B, length of outstanding leg, that is 75 into 10. By seeing this, have you observed anything? Have you noticed anything? See, this AVG and AVN both are same, this ATN and ATG both are same. Is it clear? But the values of TB1 and TB2 changes or it may varies. These answers won't be same. Please keep in the mind. So TB2 is equal to 0.9 into AVN, that is 1000, Fu 410 divided by root 3 into partial safety factor 1.25 plus ATG 750 into Fi 250 divided by 1.10. Now let us calculate TB1, that is block shear 1 and block shear 2. Now I am going to calculate block shear 1, 1000 into 250 divided by root 3 into 1.10 plus 0.9 into 750 into 410 divided by 1.25. If we divide with 10 power 3, 352.6 kilonewtons. Now let us calculate this one. Design strength of block shear 2, 0.9 into 1000 into 410 divided by root 3 into 1.25 plus ATG is how much? 750, I think 750 into Fi 250 divided by 1.10. If we divide with 10 power 3, 340. So TB2, that is design block shear 2, is 340.88 kilonewtons. So if you observe design strength block shear 1 and design strength block shear 2, which is smaller? Whether 352 is smaller or 340 is smaller? So 340 is smaller. So we are going to use 340. So design strength due to block shear TB2 is equal to how much? 340.8. So what is the last step? Step 10, I think. Step 10. From design strength of gross yielding section, we got answer as 375 kilonewtons. from design strength due to rupture, we got answer as 472.5 kilonewtons or 3 kilonewtons. The last one, the design strength due to block shear, that is how much? 340 kilonewtons, 340.8 kilonewtons. So if you observe, whichever is lesser among them, that will be the design strength of the given plate. So 347 is less than 472, but 340 is less than 375. So the design strength TD is equal to 341. That is 340.8, approximately 341 kilonewtons is the design tensile strength of our plate. Is it clear?